calculate the relative abundance of each isotope. That is, gallium exists as two isotopes, 69 gallium and 71 gallium. These two isotopes of gallium exist as the fractional abundance of 68.9 for the first isotope and 70.9 for the second isotope, that can be expressed as atomic mass unit. So these two isotopes has also average atomic mass 69.7. Based on this given, you can calculate the relative abundance. Relative abundance means F1 and F2. Let us see. What about the given? Given A1 refers to 68.9. What about A2? A2 means atomic mass of the second isotope, 70.9. What about F1? F1 is calculated. F2 also calculated. But atomic mass unit, that means atomic mass unit of gallium is given, it is equals to 69.7. Based on this given, you can calculate F1 and F2 as follows. Let's see, atomic mass unit of gallium, which is equals to A1 F1 plus A2 F2 per 100. There are two isotopes, you can use this formula. Then substitute, but atomic mass unit of gallium 69.7, which is equals to A1 is given 68.9 times F1 plus A2 is given 70.9 F2 over 100. Take recross here, recross 69.7 times 100 is equals to this one, and 68 point F1 plus 70.9 F2. Here the sum of F1 and F2, which is equals to 100. This implies that F1 is equals to 100 minus F2. You can use this representation about this formula and substitute this 100 minus F2 in terms of F1, which is equals to 68.9 in terms of F1, substitute 100 minus F2 plus 70.9 F2, which is equals to 6890 minus 68.9 F2 plus 70.9 F2. Okay, subtract and connecting like terms. 6890 minus 68.9 plus 70.9, the remaining 70.9 minus 68.9, 0, 2. What we call 2F2. What about the remaining 6,970 minus 6,890 equals to F2. What about this one? F2 is equals to what? F2 is equals to 80. Then divide by both sides 2. Can get F2 equals to 40%. What about F1? F1 equals to 100 minus F2. So it is equals to 100 minus 40 is equals to 60%. So the fractional abundance of the first isotope 69 gallium is this one, and F2, that means 71 gallium is 14. So you can calculate like this the fractional abundance of F1 and F2 for gallium. Second, let us see a grammatic representation. Okay, Bohr, which is a scientist that designed or established energy levels, energy levels or main shells. That means K shell, L shell, M shell, N shell, like this. This shells has a maximum of electrons. That means K shell represents the first shell, L shell represents the second shell, third shell, fourth shell. The maximum electron of each shell can be calculated by the formula. You know this formula from the log rate to n square, where n refers to the number of energy levels. Let's see the maximum electron which is held by K shell. K shell is the first shell. You can use this formula to n square. Then substitute 1 in terms of n, 2, 1 the whole square equals to 2 electrons. The same is true for L shell or the second shell. 2 n square, 2 into 2 the whole square equals to 8 electrons. Third, 2 n square, 2 into 3 the whole square equals to 18 electrons. The fourth one, 2n square equals to 2 into 4 the whole square, which is equals to 32 electrons. So each shell has a maximum capacity of holding electrons. K holds 2, 8, 18, 32 electrons. Let's see examples for the Bohr diagrammatic representation. Example draw. The diagrammatic representation of let's say A 28, 14 silicon, and B let's take 39, 19 potassium. We can use this using main energy level, K shell, L shell, M shell. K shell holds a maximum of 2 electrons, so let us put 2 electrons under K. L holds a maximum of 8 electrons. M holds a maximum of 18 electrons. But how many electrons are left? 4 electrons are left, so you can put 4 electrons under M. So this you can represent this using diagram notation, what we call. You can write like this: first shell, second shell, third shell. The first shell is K shell holds 2 electrons. You can put like this 2 electrons. The second shell, L shell holds 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons. And the last shell, M shell holds 4 electrons. You can write like this, what we call diagrammatic representation of electron configuration. What about potassium? K holds a maximum of 2 electrons, L holds a maximum of 8 electrons, and how many electrons are remaining? 9 electrons are remaining. So 9 electrons can be put under N, but this presentation is not correct because for main group elements, the valence electron is equal to the group number and the period number. The valence electron is equal to the group number. But in the periodic table, the groups are represented by Roman number 1 up to Roman number 8. This is representation not correct. So you can write this as 8, then add n shell 1. 2, 8, 8, 1 is the correct configuration for potassium. So you can represent this as this nucleus the center of an atom, in the first shell, second shell, third shell, fourth shell. So the first shell holds 2 electrons, the second holds 8 electrons, holds 8 electrons, the third also holds 8 electrons, and the last shell holds 1 electron. So you can represent like this. Generally, the shell can be represented as nucleus, first shell, second shell, third shell, fourth shell. The first shell is K shell, second N shell, N shell, N shell, O shell. Then K shell means 1, L shell is 2, M shell is 3, N shell is 4. You can represent like this historical diagrammatic representation of electric configuration based on the Bohr's establishment of the Bohr's idea. Now let us see the other point, electron configuration with respect to quantum mechanical model of atom or quantum theory. Okay, quantum established subshells. Quantum established subshells. What are subshells? Subshells are S, P, D, F subshell. But Bohr doesn't design such type of electron configuration or SPDF arrangements. Before that, let us see principles of electron configuration. Principles of electron configuration. You know that there are 3 common principles about electron configuration. Aufbau principle or building up principle, Pauli exclusion principle, and Husserl principle. We will focus on the first principle, which we call Aufbau principle. Aufbau principle. Aufbau principle states that the lowest energy orbitals are filled first before entering into the higher energy orbital. The lowest energy orbital violets are filled first before entering into the higher energy orbital is what I call the assessment of Aufbau principle. It is called as building up principle. Building up principle. Before build the first, then goes to the second. This building up principle arrange the subshells like this. Step 1 is 2s, 3s, 4s, 5s, 6s, 7s. And the second shell also holds the other orbital, that is p. You can write as 2p, 3p, 4p, 5p, 6p, 7p. And the third shell, that is n is equal to 3, holds another orbital d. 3d, 4d, 5d, 6d, 7d. The fourth shell also holds another orbital, that is f. You can write as 4f, 5f, 6f, 7f. So in order to get the arrangement of this filling of orbitals, you can show by using this arrow. You can draw like this in order to get the order of filling electrons. How to arrange this filling of electrons? You can start from 1s, then 2s, 2p, 3s, 3s, 3p, 4s, 1s, 2s, 2p, 3s, 3p, 4s, 3p, 4s, then 3d. Can continue like this. This is what we call the order of filling electrons. The same as that of main energy levels: s orbital, p orbital, d orbital, and f orbital holds a maximum of electrons. S orbital holds a maximum of 2 electrons, p holds a maximum of 6 electrons, d holds a maximum of 10 electrons, and f holds a maximum of 14 electrons. In addition to maximum electron, you can use this as maximum electron. There will be number of orbitals also. Number of orbitals. Number of orbitals are obtained by dividing this maximum electron by 2. You can use 4s 1 orbital, 4p 3 orbital, 4d 5 orbital, then 7 orbital. Orbital means the region where the probability of finding an electron is maximum, is what we call orbitals. Let us see this with some examples. Let's see these examples with SPDF configuration. 8 electrons. You can start from the ordering of filling electron, the lowest energy level, 1s, 2s, 2p. It has put the maximum electrons held by s and p. 2 electrons, 2. How many electrons are remaining? There are what? 4 electrons are remaining, and then puts at p. So you can write the configuration of oxygen like this. You can convert this into main energy levels. That means K shell, L shell, M shell, N shell. The first shell, 1s, holds 2 electrons, 2. The second shell holds 2 electrons for 2s and 4 electrons for 2p, totally 6 electrons. You can write as 2, 6 for oxygen. The second calcium, you can follow the same as for the second, and the first, 1s, 2s2, 2p6, 3s2, 3p6, you can use 4s2, 2, 2, 6, 10 electron, 12 electron, 8 electron, 20 electron. You can convert this as main energy level. The first shell holds 2 electrons, you can write as 2. The second holds 2 plus 6, 8 electrons, and the third holds is 2 plus 6, 8 electron, and the fourth shell holds 2 electron, 2, 8, 8, 2. The third one, magnesium, it loses 2 electrons. That means 2 electrons are lost from 12 electrons. So you can subtract 2. 1s2, 2s2, 2p6, 2p6. This implies that 2, 8. Because 2 electrons are lost means 10 electrons are arranged in SPDF configuration. The last one, 26 iron. Iron has 26 electrons. So you can write like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. After 4s2, how many electrons are there? 20 electrons. How many electrons are remaining? 6 electrons are remain, so you can use 3d6. D holds a maximum of 10 electrons. So you can convert this into main energy level as the first shell holds 2 electrons, the second holds 8 electrons, and the third 2 plus 6 plus 6, 40 electrons, and the last shell for the fourth shell consists electron. Can convert like this. This implies that let's see with diagrammatic representation. The nucleus at the center of an atom, which is a heavy region of atom, including proton and neutron. Let's see this one. This is the first shell, second shell, third shell, fourth shell. The first shell possesses one orbital only, 1s. The second shell possesses 4 orbitals, s and p. It has s and p orbitals. The third consists 3p, 3d. That means s, p, d. The fourth possesses 4 types of subshells, s, p, d, and f. Each shell has a maximum electron. That means s holds 2 electrons, p holds 6 electrons, and d holds 10 electrons, and f holds 14 electrons. So in the first shell, how many electrons are there? There are 2 electrons. In the second shell, there are 8 electrons. In the fourth shell, not the fourth, on the third shell, how many electrons are there? 8 electrons. In the fourth shell, there are 32 electrons. You can arrange the electrons like this. Now let us see the noble gas configuration. In addition to subshell notation, you can use noble gas configuration or write in short. Let's see some example. Noble gas as a core configuration. Noble gas as a core configuration. You know that core means center. Noble gas as a core. Let's take example 3-methane. How to write the configuration of methane using noble gas as a core? You can use noble gases lower than methane or lower than 3 atomic number. That is, you can use helium in parentheses or closed bracket. Helium has how many electrons? Helium has 2 electrons. 2 electrons. That means you can use parentheses that represents 1s2. What about the second? 2s. 2s holds what? 1 electron, because 2 electrons are represented by helium electron. Second example, let's say 9-fluorine. Okay, let's change this one. Let's say 13 ammonium. 13 ammonium can be written as neon. Neon, how many electrons does? 10 electron. Can be written as 1s2, 2s2, 2p6. This representation can be replaced by this one. After 2p, there will be what? 3s. So 3s2, then 3p1. You can write like this. This is called as noble gas as a core configuration. Now let us see some principle or principle because of stability. Exceptionalities. Why this exception is taken? Because of the stability of electron configuration. Half-filled and full-filled stable orbitals are needed to stabilize the electronic arrangement. So let's take this one. Ns2 and -1 D4 and Ns2 and -1 D9. When these configurations are faced in the problem or when you are in electrons, you can convert this as Ns1 D5. This can convert into this one. That means this configuration is what? Unstable. What about this? What we call half-filled stable. Half-filled stable. The second exception, Ns2 and -1 D9. When these arrangements are faced, you can convert this as Ns1 and minus 1 detail. This is what we call unstable also. Unstable. This is what we call full field stable. Full field stable. Or highly stable than half field. Half field. Let's take an example. T24 chromium follows this rule of configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3b4. When there is 4 electron on the orbiter, it follows like this configuration. So this can be converted into, subtract 1 electron from S, it becomes 1, and this becomes what? 5. This is the correct configuration of chromium. For the second, let's take 29 copper. This can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. This is also unstable configuration, so we can convert this as 1. This becomes what? 10. So what we call stable configuration for copper. These are some exceptions. Not only chromium in copper, there are also other exceptions like molybdenum and like silver. These are the exceptionalities that do not follow the above principle. This is all about the today's discussion of the today's lesson. Thank you so much.